Welcome, dear ladies and gentlemen, to this yet another meeting held as part of the Social Responsibility of Science series under the aegis of Poland's Ministry of Science and Higher Education. The present series is being delivered under the title SMR and AMR, Modular and Advanced Reactors for Sustainable Development. The introductory lecture was delivered yesterday. The four accompanying talks deal with specific SMR or AMR technologies as defined in one of yesterday's lectures. Today, there are three presentations of the respective technologies ahead of us. The first to go being by Mr. Maciej Skrzypek, Master of Science in Engineering of the National Center for Nuclear Research. Hello, Maciej, so good you've joined us. Good morning, hello. The title of this talk is HTGR-POLA, the Polish gas-cooled AMR. Before we actually start, let me share with you some highlights of Maciej's career. He is one of the three chief engineers who are in charge of developing the core project of the HTGR-POLA high-temperature reactor. As you will learn, the project basically consists of a number of documents. Maciej has graduated from the Warsaw University of Technology, Faculty of Power and Aviation Mechanics, where he dealt primarily with power machinery and appliances, with particular focus on nuclear power. He also studied at the Royal Institute of Technology, KTH, in Stockholm, Sweden. The one where Professor Wacław Gudowski, our lecturer of yesterday, once worked and still maintains contacts. Besides, Maciej had worked for a few months at the CEA of France, the nuclear institution. He was a 5-month trainee at the Multiphase Thermo-fluid dynamics laboratory at the University of Illinois at Urbana-Champaign, where a considerable team of nuclear experts are working who plan to construct a small AMR. Recently, Maciej had an opportunity to visit the Beijing Tsinghua University, where they have high-temperature reactors designed using a technology somewhat different to what we are going to see in a moment. Mr. Skrzypek joined the National Center for Nuclear Research back in 2017 and now is a senior specialist for research and technology there. Cutting the long story short, he has joined and contributed to a number of national and international R&D projects regarding reactors, as well as safety calculation codes for nuclear reactors, a whole lot of them, including SARWOT, ITC, INSPECT, Gemini 4.0, Gemini Plus, NARCIS, IVMR, treasure, gyroscope, easy SMR. Maciej is continually developing his competencies, including as a contributing participant in IAEA international workshops, as well as through a number of other nuclear activities. As I said, he is one of the chief engineers responsible for the development of the HTGR-POLA reactor framework project. Maciej, would you please take the floor and provide us with an outline of the technology in question? So once again, good morning, ladies and gentlemen. Thank you very much, Mariusz, for your extensive and quite exhaustive introduction. I'm Maciej Skrzypek, and with the National Center for Nuclear Research, I've been part of the HTGR-POLA high-temperature reactor team. I should like to introduce you to the project and provide you with an overall outline of the technology of this Polish-made gas-cooled advanced modular reactor. To start with, let me show you the project's logotype, which serves as a trademark registered with the Patent Office of the Republic of Poland, and which actually stands for the project's main features, starting with the name, HTGR being an acronym for High Temperature Gas-Cooled Reactor, POLA meaning Polish Atomic Reactor, whereas POLA is also a feminine name, following the tradition of our institute giving feminine names to reactors. At the logo's center, featured is a hidden, if you like, triso fuel particle as the founding principle of the reactor's safety. I'll cover this point in more detail later. The arrangement of fuel assemblies, as pictured in the logo, suggests that we have come across a high-temperature prismatic reactor, one that consists of stacked fuel assemblies, and I'll tell you more about its structure as we go along. My, portrait as a scientist has mostly been covered by Mariusz. I am a member of the Nuclear Power and Environmental Analyses Unit, UZ3, within the National Center for Nuclear Research, where I belong to the engineering team working on the reactor design in question. Importantly, the team was interdisciplinary, with 3 of our laboratories proactively contributing to the project. We used third-party services and those of our Japanese partners, of which I'll tell you more in a moment. During this presentation, which is meant to take an hour or so, I'll try to introduce you to the basics of Generation 4 reactors. My presentation is to some extent correlated with the introductory presentation of yesterday. While I try to avoid repeating things, I'm going to drill deeper into certain aspects, such as potential uses or applications of high-temperature reactors, their technological features, not to mention the history behind the technology under discussion, and also our experience record, and, last not least, the challenges we are facing. Then I'll pass on straight to the HTGR-POLA design, its parameters, safety systems, details of the model, and I'll show you some visualizations prepared based on the facility situated at the National Center NCBJ campus and simply the facilities scheme. I'll moreover brief you on the reactor's uses, what operation modes it can work in. If time allows, I'll address to an extent the computational tools we have used for safety analysis purposes, with an example of safety analysis to demonstrate the actual safety of the reactor given the possible breakdowns or failures. To end with, I'll briefly describe the schedule. We have namely completed the core project or basic design stage, covering in fact a considerable portion of the conceptual design. Still, there is a lot of work to do before the reactor actually becomes capable of displaying its technological potential within Poland. And I'll wrap up my presentation with a brief summary. Now, as regards Generation 4 reactors, well, all the 6 types have already been discussed by Professor Mariusz Dąbrowski, which was yesterday. So let me now focus on the high-temperature reactors, those that have been described as one of the most promising technologies within the Generation 4 concepts. To the right, you can see a schematic diagram showing at least 2 circuits, the primary and the secondary one. The primary circuit is cooled with helium, which allows temperatures of up to 950 degrees Celsius to be reached. The hot helium, releasing heat into the steam generator, can actually produce high-temperature steam or another high-temperature factor, like steam of the steam generator or the helium circuit again, in their intermediate exchanger. The secondary circuit can subsequently be used to generate electricity as a typical Rankine cycle, that is, by sending the superheated steam into the turbine set and then be coupled with the electricity generator, as can be seen in the central strand of the secondary circuit. However, the steam may also be used in industries, as it may provide cycle heat or process heat, as for instance low-temperature district heat. Ever since they were developed, high-temperature reactors have been consuming triso fuel, biso having been used at the very beginning for some time. Triso is highly resistant to damage and is highly capable of retaining efficient products generated within the fuel element in the course of its operation. In terms of the technology in question, the inherent safety concept comes to the fore. This implies that core meltdown cannot possibly appear, even in case of power loss or outage or depressurization of the primary circuit. The reactor will shut down automatically with no intervention from the operator whatsoever, this being one of the technology's major features, standing for its really high security. Now briefly about the prospective applications of such high-temperature reactors, the advanced Generation 4 reactors. First, they are capable of providing adequately parameterized heat to industries, chemical, petrochemical, and any energy-intensive industry, since the temperature ranges, as I said, in excess of 700 or even 950 degrees Celsius for primary circuit steam. After giving off the heat to the secondary circuit part, we can attain steam close to 600 degrees Celsius or even higher for helium-helium exchangers. This gives us almost 300 degrees more compared to what the light water technologies are capable of offering, be it SMR, that is scaled PWR, or BWR reactors, or large-scale ones whose temperatures of circuit, of steam and heat that can be forwarded ranges between 270 to 300 degrees Celsius. The secondary circuit temperature of around 600 allows for providing heat to branches of industry that involve iron smelting or generation of hydrogen by means of a specified cycle. Quite obviously, electricity production or gasification of coal. As regards lower temperature ranges, petrochemical industry and chemical paper manufacture can successfully make use of these properties. To the right, you can see a mapping of the distribution of the amounts of energy demanded by the European market. The second bar stands for the temperature range of 250 to 550 degrees Celsius as the range to be provided by a high-temperature reactor. Roughly, the demand of 87 gigawatt of heat at 550 degrees has been mapped for Europe. Hence, when implementing and then commercializing the technology, we can really see a remarkable potential of its use, be it in Poland or elsewhere across Europe. I think I now should cover the major features of the technology of our interest. As I've mentioned, the very high temperature of helium at the reactor outlet is primarily apparent. The applications in technological processes or electricity production can be notable, as I said. On the right-hand side, the HTGR-POLA diagram schematically shows the reactor as a 30 megawatt one. The primary circuit is marked in red, the section where the hot helium is directed to the steam generator, where it releases heat to the feed water, which is subsequently heated, superheated, and steam is generated, whose pressure is 13.8 megapascal and over 560 degrees Celsius. This is the secondary part, which subsequently leaves the containment and is led to the engine room. Then it may go directly to the turbine, where electricity is generated, or portions of the steam can be used to produce electricity for the plant's own needs, the remainder being sent to the reboiler, when it can be used as cycle steam, basically useful in industrial processes. Let me draw your attention again to the high safety offered by this technology. This is based on a number of elements. I will specify using the subsequent pictures. The basic thing is the fuel's high resistance to high temperature. The same is true for all the materials used in the core. Even in extreme emergency, under really tough conditions, the core wouldn't melt. However, the other aspect of any possible events that might happen in the course of the reactor's operation, such as temperature unexpectedly going up, is that the reactor is resistant because of its negative reactivity coefficient, which practically means that the growing temperature actually quenches the nuclear reaction, which obviously reduces the reactor capacity whilst also reducing the temperature of fuel rods and components. The use of TRISO implies excellent retention effect for the potential fission products generated within the fuel, and on this level of fuel element, most of them are retained within the fuel, never even getting into the primary circuit. Another advantage is that this reactor makes use of well-tested technologies, not only those of high-temperature reactors, but also those of gas-cooled solutions, such as gas and graphite reactors, or those using gas as the coolant. Classical solutions related to steam generators, blowers, or helium production assemblies, which are commercially available, have been taken advantage of. POLA has an important feature of load adjustability. It can basically flexibly adjust its power rate to the actual power grid requirements. The operation range in this respect is pretty wide, from 30% to 100% of the reactor's nominal power. Importantly, the water demand is rather low compared to water reactors, as we have applied fan cooling towers, dry instead of wet ones, and this contributes to reduced water consumption because of limited access to water sources within the facility.
Czyli też ograniczenie wody i z uwagi na potencjalnie ograniczone źródła na terenie obiektu. Wspomniana wcześniej
The scenario of core meltdown, impossible as it is prevented due to the following factors. Compared to light water technologies, the underlying concept here is very different. And what I mean by that is primarily a low power density, almost 2 orders magnitude lower than the one in light water reactors. Consequently, the decay heat is reduced. It gets proportionally lower after the shutdown with use of reactivity control systems, or caused by the negative reactivity coefficient. At the very beginning, once the reactor is shut down, the power drop can be typical, like 7 to 5%, then decreasing exponentially to 1%, and then tenths of a percent, this being much less power to dispose of compared to light water technologies. Moreover, the low density of the structure of the core itself is due to the use of several materials around the fuel, while helium itself is of small thermal capacity. Graphite, the material used in the core's construction, has a considerable thermal capacity. Its thermal characteristics are very good, including thermal conductivity, and primarily it is resistant to high temperatures. All in all, it perfectly fits as the reactor's construction element. Now again, about TRISO's resistance to high temperatures. We have assumed 1600 to 1620 degrees Celsius, depending on the literature. 1600 is a critical value that limits the operational conditions, the maximum temperature of the fuel while in operation or under failure, the one that shouldn't be exceeded. In addition, core meltdown is to be inhibited by the slender geometry of the pressure tank, basically the ratio of core height to core diameter. Furthermore, the surrounding safety system absorbs heat from the pressure tank, of which I'll tell you more in a moment. And this continuous absorption keeps the fuel's maximum temperature relatively low. Importantly, the modular reactor implementation concept is founded on a module-based approach. Rather than building a possibly large high-temperature reactor, the demand for higher amounts of power is to be satisfied with use of several modules, that is, small reactors of 200 to 250 MW each, rather than by constructing a single 1.5 gigawatt reactor. The safety philosophy behind such modular reactors is based on the defense in depth concept. In the case of POLA, TRISO, the fuel is actually the major barrier to the retention of fission products. This is coupled with the fuel assembly structures, cooling circulation system, and the containment. The latter is obviously made of concrete, but moreover, it is kept under a slight under pressure, filtered and situated under the ground. Thus, a number of potential accidents get prevented, or at least restricted. As opposed to light water technologies, the system I actually meant while mentioning the slender geometry thing is worth pointing at, namely the reactor cavity cooling system, or the RCCS. This safety system is a sort of counterpart of the coolant injection systems in light water solutions. The technology we have developed has no such coolant provision system in place. Instead, we have designed an external cooling system which uses mechanisms of tank heat radiation or convection around the tank into the RCCS panels. If you take a look on the right, here is a diagram specifying the temperature range in question. The mean temperature in the course of the reactor's normal operation is approximately 850 to 900 degrees Celsius, the maximum for a fuel component being roughly 1000 degrees Celsius. You can see the 1600 limit, as mentioned before, with a pretty large margin with respect to this conventionally agreed value, and with respect to the silicon carbide limit in excess of 1000 degrees Celsius. As I said before, HTGR reactors, whether experimental or commercial, have been implemented and applied in the past. Hence, we've placed a bet on this particular technology, since because of its high TRR coefficient, it has a proven record. It first appeared in the form of spherolytic or prismatic deposit technologies as applied in China, Japan, the US, and Germany, where it saw a powerful development. Rather than modular reactors, those were high-power technologies, the concept that developed in the 1970s, which sought to produce high amounts of electricity and heat. Although quite successful, the approach changed with time as basically inherent safety of the reactor came to the fore. Based on the 10 megawatt HTR-10, a research reactor still operating in China, Chinese engineers developed a high-temperature reactor called HTR-PM, 250 thermal megawatts, with a capacity to generate roughly 210 electric megawatt based on two reactors operating with one turbine set. This technology has been succeeded by HTPRM-600, which consists of 6 instead of 2 HTRs, again connected to a single turbine set. In the modularity concept, one block comprises 6 reactors. At the moment, 2 such blocks, with a total of 12 reactors, are being implemented in China, and those are ball-type reactors. How did those projects develop? Let me use the Chinese examples, or those of Japan. Our national center collaborated with the Japanese Atomic Energy Agency, mind you. Basically, the task is to turn a research reactor into a commercial reactor. It is quite a long way to go, and therefore the HTTR in Japan or the HTR-10 in China first attained their criticality at the turn of the century, and it took 15 more years or so to put an operational commercial version in place. To build a commercial reactor straight away is perceived as a somewhat risky venture industry-wise. Hence, the need for a research reactor that allows to exclude certain shortcomings and other problems on a small scale, demonstrate the operationality, and only then to apply the concept at a commercial level. In Poland, this approach enables the stakeholders to talk to those in charge, to actually make the state authorities such as the nuclear regulatory authority as well as industry aware of the technology, demonstrate to them its safety features and economics, the cogeneration potential based on the use of high-temperature steam in a variety of sectors and purposes. To this end, the research reactor ought to be furnished with as many commercial reactor features as possible and made fairly easily scalable to a higher power reactor. With our HTGR-POLA example, we have had a six-fold increase in power into 180 megawatts. The HTTR operated in Japan has also been developed into a commercial technology based on a reactor of up to 250 megawatts.
Japonia decyduje się też na rozwijanie tej technologii komercyjnej o reaktora o mocy do 250 MW.
Now about the actions and research carried out on HTGR at the National Center for Nuclear Research. Having said that, to actually implement the technology, one needs years of effort. The technology in question has been under development at our institute for quite a while now. We've been in touch with it, so to put it, for a decade now, really. In 2017, we got involved in a European project to develop a Gemini Plus reactor as part of an international consortium. The National Center was the project's leader, and we demonstrated the reactor's cogeneration potential, taking advantage of the technology, showing its safety, robustness, and teaching ourselves how to design such a reactor, how to analyze its safety features, and primarily involving ourselves in an international milieu, drawing upon our French, German, and Japanese colleagues' experience. As a follow-up of that project and the National Center's engagement, a national HTR was developed as a pre-concept, or the first tangible Polish-made product in view of a future HTGR. That was back in 2019 to 22. Then, as a follow-up of that one, a conceptual design and subsequently the final design was developed of what was named HTGR-POLA, being our domestic product that was developed in 2022 to 2024. The final design has been the major achievement, along with items of an initial safety report and the preparation and construction at the National Center of materials testing laboratories, where structural elements of fuel associated with the technology are tested.
I tutaj, tak jak wspominałem, współpraca z japońską
Our
agencją
cooperation
atomowej
with the Japanese Atomic Energy Agency, JAEA, as part of the 2022-24 project proved very close. Let me highlight that already in 2017, based on the agreement with this particular institution, our contacts and collaboration with their engineers were really close. They would repeatedly visit our national center, willingly sharing their experience and expertise regarding high-temperature technologies. Now, what's the mission of the demonstration reactor known as HTGR-POLA? Is apparent in its main functions, actually 4 of them. First, competence building, based on the perspective of development of the demo reactor and on the design process of its commercial counterpart. We have shown that designing competences can be attainable. While designing, licensing ought to be always borne in mind as the next step of the process. While designing, the related supply chain should be taken into consideration as well. And as much as the demo reactor is the first of the kind, and indeed the first and only, keeping in mind the solution's modularity, the supply chain has been mapped for the elements and components indispensable for the technology concerned, based on the need to ensure a high rate of supplies from basically the local market, this being highlighted as a competence building aspect. Next, construction and operation are very important competence building elements. As the National Center, we are presently running this Poland's only active research reactor in a close cooperation with actual operators elsewhere, this giving us clues of how to become an operator and what requirements should be followed also in the design process. The other function, strictly experimental one, is the laboratories I've mentioned before. So, testing the materials, including construction materials, the fuel for its entire life cycle, the components, including measuring devices, exchangers, plus a whole set of elements to be tested. The research function concerns the safety of operation under normal circumstances and in possible failure situations, testing the passive safety systems proposed as the solution to limit radioactivity in the primary as well as secondary circuits, and very importantly, validation of computational tools. A number of such tools were validated with the HTGR. Their computational abilities checked by juxtaposing the simulation-based outcomes against those obtained based on the experimental research. One of the crucial aspects has been our cooperation with the National Atomic Energy Agency, PAA, the Polish regulatory authority, towards elaborating the framework for the functioning of HTGRs. Albeit the atomic law is transparent enough and not dedicated to any particular technology, the technical dialogue we've commenced this year with a series of meetings, 5 or 6 meetings with PAA experts, totaling 30 hours of exchange of thoughts and ideas, giving us an opportunity to present the basic design in its entirety, enabled us to share the details of the safety concept underlying the project and enabled the regulatory body to better understand our proposed technology in view of the subsequent licensing process. This first step actually enabled us to feel more certain that the project assumptions have become known to the technology's developer, and moreover, that the dialogue and cooperation with the national agency will allow to draw and establish from the oversight authority standpoint the time horizon and developmental perspectives for our technology. And one more major function being the utility function or functionality, part of which is confirming the need for the intermediary circuit effect, testing and demonstrating the coupling with the reboiler. Inasmuch as electricity production is, if you like, the conventional part of the reactor's operation, the use of cycle steam with alternative liquids, for instance, can be tested using our demo installation. We've proved capable of demonstrating the transfer and storage efficiency in this respect. I've mentioned our close cooperation with the Japanese agency and our Gemini project experience. Consequently, HTGR-POLA is based on two concepts, some of its elements having been taken over from the Gemini Plus solution, while some others have been approved by our Japanese partners. As far as Gemini Plus is concerned, with the forthcoming commercial reactor concept at the back of our heads, which would follow the Gemini Plus geometry, also the active core concept, the structure of the fuel blocks with separated coolant flow channels and separated fuel element holes within the fuel block, are likewise taken from Gemini Plus. The same is true for our proposed activity control system and dedicated fuel elements or reflector block elements, and also for the whole energy conversion system extending to heat transportation and use of the reboiler. Furthermore, certain safety systems do follow the Gemini Plus solution. As for the Japanese concept, certainly TRISO fuel follows it, as do the main cooling system, the pressure vessel and steam generation configurations. Also the arrangement of auxiliary facilities, primarily the reactor building. Here on this slide I'm showing an overall view of the respective HTGR and Gemini Plus concepts, highlighting the pressure vessel, cross-section and fuel block elements, what they look like and how they differ between one another. There are also the core maps. In Gemini Plus, the active core is placed centrally, the control elements being situated outside in the reflector, to be specific, whereas the HTTR featured control elements within the active core. Let me show you a block specimen, if you can see it, right hand side corner, being a model of the Japanese fuel block, and there's the other one of our POLA, The solution of one block placed over the other together makes up the core, which is a solution shared by the Gemini Plus and HTTR concepts. As I've said, the core as such is composed of fuel blocks. Now let me invite you to look deeper inside into the very fuel particle. TRISO namely consists of uranium dioxide particles coated by several layers. The first is pyrolytic coal, the external layer. Then comes another internal layer of pyrolytic coal. Then we have silicon carbide, which is crucial for the fuel's chemical resistance, and the outer pyrolytic coal layer, ensuring the particle's operation under high temperatures. Then there is a pretty small particle of less than 1 millimeter in diameter, which in itself forms a sort of safety containment for the fuel element inside and is placed in the fuel compact. The fuel compact is in this case a 5 centimeter high cylinder, diameter 12.5 millimeters, within which 2,500 to 3,000 TRISO fuel particles are compressed. Such compacts are directed to the fuel block with 10 to 11 such compacts inserted in a single column, as the right-hand side drawing shows. They are placed in a sort of matrix with cooling channels between them, through which helium, the coolant, runs. The compacts enclosed in the fuel block release heat to the coolant by conduction through the graphite element to the coolant that flows inside separate holes through the block. The size of the block is 36 centimeters from side to side and 60 centimeters in height. Using it, we can create an active core and a refractor surrounding it. These are the two important areas in the core, which is designed to consist of 6 fuel blocks of the sort we've seen in the picture. The cross-section to the left shows the core's structure, consisting of a total of 13 full blocks plus 6 holes related to reactivity control elements. 6 bloków pełnych, następnie 13 bloków paliwowych pełnych tworzy taki rdzeń aktywny. These 19 blocks are surrounded by reflector blocks in one layer. Both full, as in the outer ring, and with holes for control rods and regulating rods closer to the active core, marked yellow and green, respectively, in the left-hand side picture. Elements of the replaceable refractor are located in the fixed reflector structure, within which ascending channels are placed, through which cold helium is delivered to the mixing chamber located in the upper part of the upper reflector. The way the chamber is structured enables cold helium to flow through fuel elements in the active core down to the lower mixing chamber. It then leaves the pressure tank via the pipe-in-pipe connector To the right, the picture shows the reactor's pressure tank or vessel, consisting of two main components. First, the reactor head with standpipes, through which power control elements are inserted, or testing apparatus, or inspecting or metering devices. It's a sort of lid with a dozen or so standpipes on it. Second, there's the main element, which is the pressure vessel. This lower element is mounted on a bottom support whose length, interestingly, is almost 14 meters, diameter 4 meters, or together with the collar 5+ meters. These elements are obviously fully transportable. They've been designed so that they could be delivered to the construction site. This latter element consists of 3 sections welded, with the upper section forged. Having covered aspects of construction, I'd like now to talk about HTGR-POLA's inherent safety feature. So first, TRISO fuel. Having regard to all these layers, and a coated fuel particle, which is placed in fuel compacts as another barrier to possible releases of fission products, let's observe that fuel compacts are separated from cooling channels, so that the coolant avoids contact with fuel compacts or with TRISO. Columns of backup reactivity control system are placed within the active core area containing fuel elements, rather than in the reflector only. Very importantly, there's the reactivity coefficient, ensuring the strong negative fuel temperature feedback effect. Owing to considerable amounts of construction materials and graphite, the solution is characterized by very slow changes in the reactor's temperature. Even in the event of loss of active core cooling accident, the temperatures will not be growing, as you can see to the right. Instead, the maximum increase takes place within 7 to 8 hours for some kinds of breakdowns, otherwise the maximum temperature will be decreasing. The most important aspect is the passive cooling option, using the reactor cavity cooling system, RCCS. The system is meant to remove heat during the operation and in the event of breakdown. It actually functions on a 24-hour basis, ensuring removal of heat from the cavity while also maintaining the pressure tank integrity by keeping the tank's temperature below the limit for pressure vessel steel. Importantly, it also cools the concrete shaft, the structure around the vessel, so that the concrete temperature is kept up to 60 degrees Celsius. RCCS works on an ongoing basis and is designed as a hybrid system, active and passive. The active works during the normal operation, and the flow of water in the panels surrounding the pressure tank is ensured by the circulating pumps. In case of failure, such as power failure, the water gravitational, which is passively, flows through the same panels, bypassing the pumping system in the RCCS circulation. To the right, bottom picture, You can see a single diagram element standing for either the coolant's flow through upper, lower or lateral panels, and then through circulating pumps into the water storage tank, or, with the respective valves turned off, gravitational or passive flow occurs through the piping, and then heat is released to the water storage tank. The upper picture shows that the system is actually redundant, consisting of two twin systems, A and B. This safety-oriented system is multiplied, the heat release being ensured using a single cooling system. So even if one of the systems is lost, RCCS is capable of efficiently receiving heat. Yet another system is the TRISO fuel element being part of the functional containment. The design makes use of the functional containment concept, basing on the most important barrier that retains fission products inside as TRISO fuel. Then there's the graphite matrix, or the blocks, the primary cooling system, and the containment inside the reactor building, known from light water reactors. The air inside the containment is ventilated and filtered, taking account of the pressure, which is lower than atmospheric pressure. First inside the containment and then in the reactor building. The latter pressure is slightly higher, but still lower than atmospheric. Deterministic analysis of fission products releases take into consideration three barriers, including TRISO fuel, primary cooling circuit, and the containment. We lack experimental data for the graphite matrix and the graphite block, and so we employ a conservative approach by applying the three aforementioned barriers in our release analysis. Now, as far as the main parameters of HTGR-POLA are concerned, as I've said, it's a 30 megawatt reactor unit. As per the design, its expected useful life is 60 years. The active core size is 360 centimeters in height, 6 layers of 60 centimeters each, 160 centimeters being the active core diameter. Surrounded by replaceable or fixed reflective blocks, it makes the vessel diameter slightly in excess of 4 meters. Important, the cold helium temperature inside the vessel is 325 degrees Celsius. The top-down coolant flow through the active core enables warming up at the helium to 750 degrees as the maximum coolant temperature. The high-temperature helium is directed to the steam generator via the pipe-in-pipe channel, as you can see to the right, where it releases heat to the feed water, which vaporizes, and then parameters of the steam are attained. Temperature 545 degrees Celsius, pressure 13.8 megapascal. The characteristic operation conditions are visible in this next slide. Without much going into detail, what we see as regards the energy conversion system is not helium let into the steam generator and releasing heat, thus enabling generation of high temperature steam, which is directed upwards through this red pipeline. The steam can be split and go partly to the turbine set to produce 11.5 megawatts of power maximum. in a condensation mode, and partly directed to the boiler, where up to 17 megawatts of high temperature heat can be extracted and forwarded for purposes of industrial processes. Here you can see the three modes I mentioned before: production of power, production of heat, including district heat, and high temperature heat generation. Specified here are system efficiency or performance figures for condensation or cogeneration. Even in the condensation mode, the system's electrical thermal efficiency is above 38% gross, slightly in excess of light water modular reactor efficiencies, but this was not what we've primarily sought. To avoid spending time on designing elements related to an unconventional island, we decided to design the most available elements. This was also meant to keep the project's value, basically in cost terms, at a reasonable level. Hence, the turbine set is rather a standard one of the fairly small turbines that can be delivered to the site. Also, the use of dry fan cooling towers decreases the efficiency, since we are dependent on the outside air temperatures rather than on a wet cooling tower system. So this particular value is not as high as it could have been either. But again, it was not a key criterion, so we didn't quite focus on increasing the efficiency in this respect either, as opposed to demonstrating cogeneration related operation modes. Here are the values for two selected modes against nearly 20 such operation modes specified. Due to time constraint, I'm just showing the extreme ones, such as the maximum heat deliverable to the industry, that is 25 tons of steam per hour, or 17 megawatts of power to meet the public utility needs of the National Center for Nuclear Research, or as a low temperature heat in a district heating system. Now I should like to show you some visualizations of our HTGR-POLA project. To the right, on the bottom, you can see the entire reactor installation consisting of two basic parts: the nuclear island, marked orange in this picture, which includes the reactor building, auxiliary reactor building, and spent fuel storage building, as well as conventional elements of non-nuclear island, such as the engine house, water treatment plant, auxiliary boiler house, or firewater pumping station. There's an operations building, there are conference rooms, and importantly, the electric switchboard building, cooling water circuit pumping station, and fan cooling towers. These elements are basically traditional, conventional technologies available off the shelf, of the power shelf, so to speak. Innovative elements in this project are identifiable in the reactor building and in the design of the reactor itself, rather than in the non-nuclear island facilities. The reactor building featured in the middle of the picture consists of an above-ground and an underground section, with most components of the reactor located in the latter. The bottom floor is at the level of minus 25 meters, so the entire reactor, the cavity cooling system, steam generator, spent fuel storage areas are all placed below the ground level, which obviously enhances the safety of primarily the core, preventing external dangers. Now a few cross-sections of the buildings concerned. The reactor building is situated under the ground. The steam generator
Poszczególne budynki właśnie
is
w planie
featured
obiektu.
in the central area
Budynek
and
reaktora
connected
jest umiejscowiony pod ziemią.
with the pressure vessel
Jak
via a
w
conduit.
środkowej części jest umiejscowiona tutaj wytwornica pary połączona łącznikiem z zbiornikiem ciśnieniowym.
The blue marks the RCCS, the absorption of afterheat, the system that surrounds the pressure vessel and absorbs heat from it. To the right is a view of the engine room together with the reboiler set situated on the left. Now, what does it look like in a nuclear facility plan in relation to the reactor's location within the national center area? All the buildings have been designed and adjusted so as to fit the available area. So the facility has taken approximately 3 hectares of land, 250 times 130 meters in size, including the fence and the green space around the facility. The area consists of a conventional nuclear island and demonstration facilities where high-temperature heat is transferred to industrial installations. Based on the model I showed you a moment ago, rendered have been some very nice visualizations showing the reactor's location within our campus and allowing to see the buildings, their dimensions, the sizes of installations compared to those of HTGR Maria. Some exemplary research and analyses. Here just the outcomes are quoted, but let me brief you on the spectrum of analyses carried out. These include neutron analyses using dedicated computational tools such as Serpent, enabling to calculate power distributions, core composition, and a number of other important ratios or coefficients related to power generation. Heat flow analysis tools, American, French, the CFD approach that was applied at the design and safety analysis stages, calculations of the releases using appropriate tools, probabilistic analyses enabling the demarcation of the planning zones around the nuclear facility.
Czy analizy probabilistyczne pozwalające na wyznaczanie stref planowania wokół obiektu jądrowego. I teraz myślę, że to, co jest też bardzo interesujące dla Państwa, to tak jak powiedziałem, dysponujemy pewnymi narzędziami, dzięki którym możemy obliczyć.
Now, a thing which I hope may be of interest to you. We have at our disposal certain tools that allow us to calculate temperature, pressure, and flow rates in individual elements of the primary and secondary circuits. This screenshot visualizes a temperature distribution for the core in a steady state, that is, under normal operation at full power. At the initial stage of the reactor's life, the maximum temperatures are not in excess of 1000 degrees Celsius, the hot helium leaving the pressure tank being 740, 741 degrees. The parameters to be directed to the steam generator. This is the fragment where the pressure tank is visible, the cavity and the RCCS. Looking deeper to the central fuel column and all the fuel elements, the mean temperature is below 900 degrees Celsius, so more than 70% of the core is kept in a relatively low temperature, with just one unit exceeding 1000 degrees while in operation. This ensures a considerable safety margin. With not much time left, let me mention the design analyses.
nazywa z zachowaniem szczelności układu, czyli taki
I've
przykład, gdzie
chosen
po
two
prostu
examples.
buchawa
One is
zostaje wyłączona,
analysis of the
oraz
loss
drugi
of
typ awarii
forced
to taki
coolant flow,
takie podejście, gdzie
keeping the
tracimy
system leak
wymuszony
tight
przepływ
when the
łacicy
blower
przez
gets
rdzeń,
switched
ale
off.
dodatkowo tracimy również
The other
integralność
type of accident
tego
is when the
biegu
forced
pierwotnego
coolant flow
i podziwo
through the core is
opuszcza bieg
lost
pierwotny,
as the
następuje
primary
rozszczelnienie
circuit
tego układu.
integrity. The coolant leaves the primary
Mimo tego,
circuit
że są
and
to
the
takie
system gets
naprawdę
unsealed. Although
jedne
these are
z
some of the
bardziej
most serious accident scenarios,
analiz, czy takich
the temperatures would then only increase by approximately
widzimy, że
100 degrees
temperatury w
Celsius,
trakcie takiej awarii wzrastają, tak jak mówiłem,
retaining a
niemal do 1000
considerable
stopni Celsjusza,
temperature
zachowując
safety
bardzo duży
margin of
margines
up to
bezpieczeństwa temperaturowych, 1600 stopni.
1600
Żadna
degrees,
część paliwa nie zostaje przegrzana
with
w
no
trakcie
part of the
tego,
fuel getting
takich
overheated as the
awarii.
failure occurs.
Mamy bardzo dużo czasu, tak jak widzimy
There's a
nawet
plenty of time, up
pośrednio
to
godzin na
7 to 8 hours, to
reakcję,
respond by trying to
przywrócenia
restore
takiego
power,
zasilania, chłodzenia, ale
the
również przeprowadzono
cooling.
testy, właśnie czy to w
In
Chinach, czy w
China and
Japonii,
Japan,
reaktorach
tests
testowych,
have been
reaktorach
carried out
produkcyjnych,
with use of the
że ta
test
utrata takiego
reactors
przepływu chłodziwa
or even a commercial reactor,
spowoduje to samoistne
showing
wyłączenie
that the loss of
reaktora i
coolant
nagle też
flow
spadek
would cause automatic
temperatury.
shutdown of the
Widzimy
reactor and a
te
decrease in
zaznaczone
temperature. The ranges are shown in the
Już
table here.
naprawdę kończąc, oczywiście
As a
nasze
final
rozwiązanie, czy
remark, we
dzisiaj,
do
czy w
promote our
trakcie tych
solution by
kółek
way of
naukowych
presentations like the present
popularyzujemy
one,
właśnie,
or
czy
at
spotykając się z
science
Państwem, czy
picnic
przekazując właśnie
events,
wiedzę w trakcie
meeting
jakichś
people
prezentacji,
and
ale
talking to
również
them.
zrobiliśmy małą taką wystawę
Among other
w jednym
things,
z
we've
centrów
prepared an
badawczo-rozwojowych
exhibition
Brony.
at the
Mieliśmy
National Center,
przedstawiana na
which was also
uniwersytecie,
shown
na
at the
Wydziale
Warsaw
Fizyki,
University's Department of Physics,
gdzie
where
wydrukowaliśmy
we
modele w
printed
oparciu o naszą dokumentację
out
poszczególnych
models
elementów,
based on
komponentów
our
i
documentation
żeby
covering
zwizualizować, jak
individual
takie,
elements and components.
taki reaktor wygląda. Jeżeli Państwo byli bardziej zainteresowani,
To visualize
odsyłam
what the
do
reactor
artykułów,
under discussion actually
które
looks
udało nam
like.
się
For those of you who are interested, I'd like to refer you to the papers our team has
gdzie są
published
również
describing
nie
the
tylko
basic design
projekty
and
testowe,
results of
jest
the
opisane, ale również
analyses.
wyniki poszczególnych
Mariusz has
analiz.
recommended it
Też
already
wspominał, ale
yesterday,
zachęcam
and
również do
let
odświeżenia
me again draw your attention to the
pozyskania
publications,
informacji o reaktorze
bulletins, and
w szkole
booklets by
eksploracyjnej
NEA or
NEA czy
IAEA.
IEA. Tutaj podałem link
Here
od razu
is
do
a link to the
systemu ARIS.
ARIS
Możemy tak naprawdę
system,
zobaczyć wszystkie parametry
where you
oraz
can take a look
bezpieczeństwa tego
at
reaktora.
all the
Co
reactors,
dalej? Czyli tak
parameters,
jak mówiłem,
and
jesteśmy
safety
gdzieś pomiędzy,
functions.
już wiele etapów za
Well,
nami,
what's
ale
ahead of us now?
jak
We've
widzimy
been
na tym
through a number of
środku, to
stages.
na
The
razie
basic design
udało się
has been
opracować ten projekt
completed as of
podstawowy w zeszłym roku, 31 grudnia, w połowie
the
tego roku został
31st of
wybrany
December
przez ministerstwo,
2024. In the middle of
a
this year,
widzimy, tak jak
it was
od
officially
maja
accepted by the
mieliśmy ten
ministry.
dialog
Since May this year, we've been
techniczny z
in a
Państwową Agencją
technical
Atomistyki,
dialogue with
więc
the National
od
Atomic
przyszłego roku
Energy
mamy
Agency.
nadzieję
Next year,
na
we
wznowienie
hope to
prac nad
continue our work on
projektowaniem,
the technical design
nad
and the
pracę nad
detailed
projektem
design.
technicznym, a
As a
następnie
further
wykonawczym.
prospect, follow-up licensing work is to be done.
Równolegle pracę nad
The expected
funkcjonowaniem
construction period
i
is 4
zakładamy, że w
years
Polsce
roughly,
data
this being
budowy takiego
strictly associated
reaktora,
with our
przy czym
further
tak jak
work on
jest
the
to bardzo
technical
silnie
design. So
powiązane
if we
z
start again
początkiem
next year,
dalszych prac nad projektem
we should be on
technicznym,
schedule
więc
with
jeżeli
these
zaczniemy w
specified
przyszłym roku,
periods.
zakładamy takie okresy,
But we do
ale
count on
też bardzo
contributions
silnie
from our
liczymy na
partners we've been
naszych
cooperating with,
partnerów.
such as
Już wcześniej
IAEA
czy
or
mieliśmy okazję
Projekt
współpracować,
Katowice.
jak IAEA czy Projekt Katowice. I tutaj taki we współpracy z tymi instytucjami myślę, że taki harmonogram mógłby być jak najbardziej dostępny.
Shortly to summarize, let me stress that this is a reactor that, as Mariusz said yesterday, has been designed with a 50% Polish intellectual output. The first such project since the Maria reactor. It was developed resulting from almost 3 years of meetings and discussions held in Japan, in Poland, the trips, exchange of experience and expertise with the teams, a total of 18 volumes of documentation, over 3,000 pages of technical descriptions, drawings, models of all the components, some of which have been printed out. We've developed the characteristic operation modes I've mentioned earlier,
jak tutaj dzisiaj omawiany,
arriving at the present
SMR-y,
stage was
MMR-y,
enabled
w ogóle
by stable
zaawansowane
funding, cooperation
reaktory,
between the
duże
industries
reaktory
involved,
muszą
by
mieć
the
jakby
advantage
kolejne
taken of the
eksploatacje,
experiences
musi
of international
zostać
R&D teams.
ponawilana przez
We
centra
constantly bearing in
nowego,
mind that any
więc
reactor, be it the one in question,
najważniejsze
as
jest
well as any
bezpieczeństwo
SMR,
i
MMR,
żeby
or
nasza
any
Kungliga
advanced
Tekniska
modular
Högskola
type, and the large
opiera
reactors
się
all
według
have to
polskiego
obtain an operating authorization to be issued by the
dziękuję
head of the
Państwu za uwagę.
Nuclear Regulatory Office. Safety first, and I'm positive that our HTGR-POLA reactor is founded upon this very idea. Thank you very much for your attention, and I'm ready to take your questions, if any. Thanks so much, Maciej, for this pretty detailed talk that has touched upon so many aspects of your project. We regretfully have to finish at this point because in a quarter of an hour's time we'll be talking about yet another AMR technology, namely a fast lead-cooled reactor. So thanks once again for your excellent presentation. My sincere thanks extend to you, our dear audience. As you can see, you're being hosted by Professor Jerzy Stelmach, Eureka Foundation. Please continue watching us on YouTube. I'm talking to you now from our Szczecin headquarters. The exhibition setting accompanying me here is partly devoted to nuclear power industry, the TRISO fuel particle and other related elements featured. So thank you very much, and do join us for the coming lecture, which is due to start in